Okay, so trends in ionization energy. We have already been introduced to the term ionization energy. I'm going to put the definition down again, even though we've already wrote it down when we talked about the formation of ions. Ionization energy is that energy required to remove an electron from an atom. And technically, it's the energy required to remove just one electron from an atom. We've already seen with our metal ions that sometimes we just remove one if it's group 1. To make a stable ion, if it's in group 2, we'll remove 2. If it's in group 3, we'll remove 3. And I've already told you that it takes energy to remove an electron, right? If you've got anything that's held together with an attractive force, it takes some energy to pull that away. Technically, the ionization energy is the energy required to just take one electron away. And it is a direct measure of how strong the electrostatic force is. If the electrostatic force on that outer electron is strong, then how much energy is it going to take to remove it? And I don't need a number here. I just need an adjective to describe how much energy it's going to take to remove it. If the force is strong, how much energy is it going to take to remove it? A lot. Thank you. It's going to take a lot of energy. And if the force is weak and it's not being held with a great force, how much energy is it going to take to remove it? Less. Not much. Little. A very little bit. And so the ionization energy is a direct measurement of how strong we hold on, or the atoms hold on to their electrons. And we already know how to argue strength of force. So if we can argue strength of force, then we can easily argue ionization energy, because it just goes hand in hand. If there is a strong force on the valence electron, then there is a lot of ionization energy. It's going to be a high number. And if there's a weak force on the valence electron, it's going to be a small number. All right? How do they measure ionization energies? They can measure ionization energies in an experiment that uses electricity, kind of like a Tesla coil. All right? But like a Tesla coil kind of overdoes it. That's like taking a sledgehammer to put in a nail for a painting, right? You'd never use a sledgehammer. To do that, it would be a little overkill. You'd go right through the, right through the drywall, right? When I use the Tesla coil, I'm not just removing one electron from the atoms in the air. I'm ripping off pretty well all of the electrons. It's too powerful. But if we had a device that we could slowly turn up the electrical voltage that's pulling on the electrons in an atom, then we would eventually get to a point where those first electrons start to be pulled off. All right? We could do it with an experimental setup where if we had a tube, all right, and we've seen the tubes that had a particular gas in it. Let's say we put some hydrogen gas in there, and we put some voltage on there, and we make it variable. This symbol means that we can turn up and down the voltage. And we put a little ammeter in there, a little meter that measures the flow of electricity, a current flow. And if you slowly turn up the electricity, that dial doesn't move until the first electrons start coming off of those atoms. And when those first electrons come off, the ammeter registers a little flow of electricity. And from that voltage, we can use our equations for electricity. If you're taking physics with Mr. Petrus, you'll learn those equations, and we can easily figure out exactly how much energy it took to rip off those electrons. Okay? So we can measure it very easily. All we got to do is change the atoms in here, and we can measure the ionization energies, how much energy, electrical energy does it take to pull that electron away. All right? And we can measure that easily. Let's talk about the trends then. Even before I put on an example, I think we could explain this. If the strength of the pull or the strength of the hold determines, right, how much energy you need, let's talk about it. As I move down the periodic table, what should happen to the amount of energy needed to rip off that first electron? What should happen to the ionization energy? Ionization energy is the amount of energy needed to take that electron away. You can imagine it as being how hard you'd have to pull some magnets apart. All right? If the force on the magnets is strong, how much do you have to pull? Hard. Right? If the force on the magnets is weak, nothing. You imagine how hard you'd have to pull to take an electron away as you move down the periodic table. That's going to be the effect on the ionization energy. Because how much you have to pull is a direct measure of that energy needed to take it apart. So what's going to happen as we move down? Lithium, sodium, potassium, rubidium, down the periodic table. What's going to happen to how much you have to pull? Dallas? Should be less. Why is that? You give me the argument. So as you move down the table, it has more orbits. Therefore, beautiful. The electrostatic force would be less, and therefore, the ionization energy would be less. Does that make sense? Really easy to take those electrons away that are at the bottom of the periodic table. That outer electron for cesium and francium, it's hardly hanging on to that electron. It takes nothing to take it away. You've got it. You've got the trend for ionization energy. There you go. There's the lesson. It's that simple once we get the ideas. Let's talk about when we move across. As we move across the table, say boron, carbon, oxygen, over to fluorine, not necessarily these, well, this guy too, I suppose. Yeah, because as you move right, it's still going to be the case. You can still pull an electron off of neon. What's going to happen as we move to the right, to the amount that you have to pull to take that electron away? Again, remember our two possible explanations. What do you got? Why is that? It doesn't have to do with the number of electrons in the valence shell, unfortunately. There's more protons, not in the valence shell, but there's more protons in the nucleus. What does that do? It pulls them harder and in closer. What do we call that pull? What are my favorite words in these descriptions? So it increases the electrostatic force. It does pull them in closer. That's true. That's not needed for this argument, because as soon as it has a greater electrostatic force on it, what's that going to do to the amount of energy you need to pluck the electron away? Finish the argument. Therefore, yep, the ionization energy increases. There you have it. Same argument as we used for size, except now we're thinking about the pull. And now we have the trend in ionization energy. We've got it. All we got to do is write it down and do a couple of examples. Okay. Across the period. And I'm not even going to do an example. Just the trend. There it is, right there. Oh, you know what, folks? Don't write down nuclear charge. Nuclear charge and number of protons means the same thing, but sometimes we get confused when we switch it back and forth. Right across the period, the number of protons increases. The nuclear charge is just the charge on the nucleus. That is the number of protons. But I am a fan of keeping one term there, all right? Very often students will confuse the term nuclear charge and electrostatic force. They are completely different things. So if I'm marking this, right, if you're writing this down and I'm marking this, right across the period, the number of protons increases. Beautiful. I don't put check marks for each one. That's not the way my brain works, but that's the way I'm thinking. This results in a greater electrostatic force holding the valence electrons tighter, making them harder to remove. Greater electrostatic force. Fabulous. If the electrostatic force is then increased, it takes a little more energy to remove it. I like that statement there. That's not a bad one. Making it harder for them to remove. That makes you think about that pull. And therefore, this increases the ionization energy. Beautiful. Okay? So like I said, we're saying the same things over and over again. What do I have next? Do I have a cross? Let me just, hold on one second. Okay, hold on, before we do that. Underneath there, let's just put a little example. Example. The ionization energy for, well, you pick a couple of them, and you tell me. Pick a couple of elements that we can then make a conclusion of one being greater than the other. I don't care which elements. What do you got, Chelsea? So chlorine and phosphorus. Therefore, the ionization energy for chlorine is smaller. Oh, we've come so far. We've now tripped. Okay, let's remain calm. Here, Chelsea, why don't you read what we've got here? Go ahead, read it so I can hear you. Okay. Okay. Ionization energy. And you wanted chlorine and phosphorus? And what are you telling me? Don't whisper to her. That's no fun. I like it when the pressure's on. What are we saying about chlorine versus phosphorus? Someone help Chelsea here. Chlorine and phosphorus is great. Maggie? Beautiful. Therefore, the ionization for chlorine is greater than for phosphorus. Where do the wheels fall off, Chelsea? Is it in the definition of ionization energy? You don't know? All right. Well, I'm sure you'll come at lunch and we'll get to have a good talk. Now I'm afraid to ask. Is everybody okay with this? All right. As you move right, more protons increases the pull. If it's harder to remove, the ionization energy is greater. It's going to take more energy to pull that apart. Let's move on to the next one, down the group. Now notice there I've got in a larger orbit. You could just say there are more orbits as you move down. However you want to put it. As long as it's logical and contains all the data, that's all that matters. Again, when I'm marking this, I'm looking for, as you move down, there's more orbits. The valence electrons are now farther. This results in a weaker electrostatic force. If I'm making study notes for a test, I'm breaking that down into about 4 or 5 words to get that memorized in my mind. If I were to turn this into 1 or 2 words that I'm writing down on a review note, what would I put for this statement here? Yep, more orbits. If I'm breaking this down into 1 or 2 words, how could I summarize that? Yep, Maggie? Sure, electrons farther. We know that when you're writing the answer, you're going to write from the nucleus, right? But when you're studying, you can omit the obvious words because you're just quickly getting the information. How about this? Yep. Weaker electrostatic force. I might even put the weaker ESF, right? That's good enough. You can expand on that when you're writing. Therefore, IE arrow down, right? You can make that note into 6 words, and then in the end, IE arrow down, and you've got all of it, okay? And that's what you do when you make study notes. You want to get rid of the words that you know, obviously, so that when you look at it quickly, you say, yeah, I got that. Then when you get to the answer, you're able to do it. Example. Example. The IE for blank is blank then blank. So we pick a couple of them. Alyssa is staring hard at the periodic table. She must have her two favorite elements within the same group determined. What do you got? Sure, lithium and potassium. Therefore, the ionization energy for, well, you tell me how to compare these. I don't know whether you want one, how do you want to do it?
For potassium, weaker.
I don't know the sign for weaker. You want less than. You want less than. Lithium, that's okay. Lower ionization energy. Okay? More orbits. I like to think of, like francium, I like to think of francium as the delinquent parent of the atoms. It has such a weak attraction for its outer electrons, it doesn't even know or care whether that electron has been pulled away. Right? I can just imagine a police officer atom come along. Excuse me, francium, do you know where your outer electron is? I have no idea where my outer electron is. I'm barely attracted to the thing. I really don't care what it is. Got it. What's that? But it's fun to give it to them, isn't it? All right. Okay, don't need to write this down. I actually used to give an assignment where I actually gave you the data for the ionization energies, made you graph it, hand it in, but you guys were whining about too many labs the other day, so I held off on that. I was going to give you that yesterday. Anyway, if you graph it, it looks like this. And we can get some interesting information off of this. If you graph that ionization energy, and then the unit they use is electron volts. And again, the volts comes from the same idea as using voltage to pull it off. Don't worry about the unit, but it is an energy unit. But if we take a look here, you can see here, helium, neon, argon, krypton, xenon. If we compare all of those as we move down the group, look at what happens to the trend as you move down the group. What happens to the ionization energy? Yep, it decreases. That's exactly what we predict theoretically. That's what we see experimentally. And I can do that for every one of the groups. It doesn't matter whether I'm using these guys down here, because right after helium comes lithium, right? So these guys are my group ones, the bottom guys. It does go down still, even though it goes down a little less. If I now go across the period, starting with lithium all the way across to neon, so now I'm looking at lithium and I'm moving my way across to neon, you can see here there is also a trend, and I'll just go for this color here. Starting from here, you can see we've got an increase. You'll notice there are some bumps in this, and it's always after the second one, then the third. Second one, then the third. This is the transition metals, but again, we can see the trend. We can't see the second one, third one. Let's not worry about the transition metals. Second, then third. And then there's also a bump, second, third, fourth, fifth to sixth. Second, third, fourth, fifth to sixth. Don't worry about those little bumps in there. Again, I've told you that there's always some little anomalies in there, and it has to do with these subshells that I keep mentioning to you that you will learn about next year. So there are some little bumps in our idea, but in general, as you move across the periodic table, the ionization energy increases. And this is experimental evidence, which then supports our theory of the protons and the orbits. Yes? No, I'm not going to ask you to graph it. I'm not going to ask you to graph that on a test. All right? I sometimes make you do it for a little assignment, depending on what the time is in terms of my last class. We didn't do that. I'm just showing it to you now so that you can see it. So I won't be asking you to graph that on a test. Okay? Okay, let's now talk about multiple ionization energies. Now, ionization energy, pluck one away. That graph we just saw compared a bunch of different elements. where we plucked one away, and then we put in a new element and plucked one away so we could compare how they change when we change the elements. Now we're going to look at one element, and we're going to keep plucking electrons away. We're going to take one away, then we'll take a second one, and then a third. You can do that with the same apparatus. Turn it up until a little bit of electricity flows. You've got the first one. Then keep turning it up. As you keep turning it up, it doesn't change until the second one comes off. Then the little meter changes. You now have 2 electrons. Crank it up. Doesn't change until the third one comes off. Then you've got 3 coming off. All right? So we can measure how much energy it takes to pluck successive electrons away. And what we want to talk about now is what happens as we keep taking electrons off of the same atom. What happens to the energy needed to take those electrons off as we keep pulling? The example we're going to use here is 12. So we're going to be using magnesium. So you can write that down there. And we'll talk about what the first ionization energy is and how much energy it takes to take it away. So good old magnesium, 282, located there on the periodic table. We turn up the voltage, take one away. That energy needed is called now the first ionization energy, the energy needed to remove 1 electron. And the first one comes off the easiest. If it didn't come off the easiest, it wouldn't be the first one. Because the first thing to go is always the easiest thing to go, right? You see what I'm saying? If you've got a structure that has a weak beam, if the structure fails, it's because the weakest thing failed, right? So the first one comes off the easiest. And we've just looked at that. And that's not that exciting. So the first one comes off the easiest. Excellent. We're not worried that much about the first one. We just learned about it. Now let's talk about then plucking off a second one. Now, I could ask the question, is it going to be easier or harder to remove the second one? But that's really kind of an absurd question, because if it was easier, it should have come off first. So it's naturally going to be a little bit harder to pull off the second one. Why do you think it might be a little harder to pull a second electron away from a magnesium that has already lost an electron? Why do you think? Yep.
There would be more protons and electrons, so this is created.
Yeah, there is. In this case, and I've taught you, I've taught you very, very clearly that it really doesn't have to do with the number of electrons, but as it gets pulled further away, it's going to sense a +1 charge instead of it being neutral as it gets pulled away. It's a little bit like the deer in headlights, but reverse, okay? If the deer in headlights happened to, the car happened to stop, and then somehow that car's lights were changed, like it was mad, so it took its hoof and broke one of the lights. That'd be awesome, wouldn't it? Like a ninja deer. So, in other words, now the car is different. As the car then moves away, the deer's going to see something different. It's going to be only one light. If you have an atom that loses 1 electron, it's being pulled away from what was an atom and it's becoming a +1 charge. But when you pull an electron away that already has lost one, it's being pulled away, and the +1 charge is there, and it's becoming a +2 charge. And that's going to be harder. In the end, that electron is still going to be attracted to that thing, even though it's getting far away from it, because it's now overall charged. Okay? So it makes it a little harder to pull it away. Second, ionization energy, amount of energy needed to remove the second. I'm going to bring all of the bullets up because I find sometimes the animations are distracting. I'll just let you write the whole thing down and then we'll do that. Now, unfortunately, you're drawing a whole new picture and in order to understand it, so I'll stop talking for a little bit to draw. Are we going to have a test soon? We're going to have a test next Wednesday. Like no test at all until the final exam? No, that would not be sweet. You think it might be sweet, but it would result in catastrophe, especially for you, Brendan. From the little that I've known you, I have a feeling that if we did no tests, it would not be good for you. No. Yeah.
I would enjoy it.
You would. You would. Just choose not to wear them? Just choose not to wear them? Or don't have them?
Oh, boxes?
Yeah.
I don't have.
Oh.
I can see it. It's just all right.
Yeah.
You're fine.
Okay. All right. Would you like me to move you into a prime position here? Okay. The second ionization energy is defined as the amount of energy to remove the second electron. In this case, there are 12 protons pulling on 11 electrons. The electrostatic force, therefore, on that valence electron is stronger, and therefore, it takes more energy to remove the second electron. As I stated to you yesterday, and I do really want to make this clear, I told you yesterday that it doesn't matter how many electrons they are. It's just the protons it feels, and it shouldn't change because it's just 12. But again, it's as the electron gets further away that it then takes the extra energy. Because as it gets further away, it's feeling a +1 charge. It's being pulled away from an overall +1 ion, and it's becoming a +2 charge. So as that electron is pulled away to great distances, it's still being pulled back by a +2 charge. And so that's going to take more energy to get it to great distances away from the atom. The first one to come off is feeling that pull, right? Feeling the 12, and as it's pulled away, it's turning into just a +1 charge. And so that, in the end, in the long run, to make that first electron come away is not as hard as when you're trying to pull an electron away from a +2 charge as it becomes that, okay? So it's as it gets further away, it's turning into that +2 ion, and it's going to be trying to pull that electron back. And that takes energy. So the second ionization energy is greater than the third. Now, we're at our stable ion. But to continue the analysis, we're going to be evil. We're going to remove the third electron. What do you think is going to happen to the amount of energy needed now to remove the third one compared to the jump that we needed to remove the second one? Think about where we're taking that thing from. Haley, what do you think? And comparably, how much more do you think? A lot more. I like that. A lot more. Let's keep it simple. Why is it going to take a lot more? Yes. It's going to be removed from the second orbit, which is much closer to the nucleus. Therefore, the electrostatic force is much greater. And so to remove it, there's going to be a great big jump in ionization energy because now we're pulling it from the second orbit. Excellent. Good analysis. So I'll bring all this stuff up. New picture. 3 bullets. But I have 2 more bullets on the next slide, which doesn't need a new picture. It's still the same, goes the same, but I couldn't fit it all on the screen. So, new picture, taking it away from here, 3 bullets, 2 more bullets to come at the end, just to clarify things. Same effect as the last one. We're going to be pulling an electron away that is now +2, and as it gets pulled away, it's going to become +3. That's going to be harder to do. But we are also pulling an electron away from now the second orbit, which has a much greater electrostatic force, and therefore it is a big jump. It takes a lot more force to remove it. This is why we call magnesium +2 a stable ion. We haven't talked about where the electrons are going. We're just talking about plucking them away. But after this test, we're going to talk about how compounds are formed. And so the thing that's taking the electrons away in terms of magnesium is a nonmetal. Bring chlorine close to it, and it pulls the electron away from magnesium. So the reason magnesium only allows 2 electrons to go, it's not so that it's because it's happy with the full outer shell, right? But it's because if another chlorine were to come along, a third one, and exert its pull on the electron that's close to it, it doesn't have a strong enough pull to take it away. So only 2 chlorines can come along, take one, take the other. A third chlorine could come along and bump into it, but the hold on that electron in the second orbit is so strong that chlorine doesn't have a strong enough pull to take it away. So only 2 chlorines can react with 1 magnesium, and we have magnesium chloride. It's not that it consciously decides, stop, I'm out of outer electrons, thank you third chlorine, thank you for your interest, but I'm all taken care of. It's because, sure, a third one could come along and bump into that ion, but it doesn't have a strong enough force to pull away a third electron. It doesn't happen because of physics. The hold on the inner orbit is so strong, another atom can't pull it away. The chemical reaction stops. Yes? It's not that 2 hasn't, well, okay, the first chlorine comes along, right? And chlorine has a pull on electrons. We'll talk about that on Monday. The chlorine comes along and exerts a pull on the first electron. It's held easily, right? Takes it, +1 magnesium. A second chlorine comes along, bounces up against it. The second electron is still in that outer orbit. Takes it. Third one comes along, exerts a force on it, but the hold on it is great. Doesn't take it. Reaction over. Has everything to do with the fact that the inner orbits have such a strong hold on the electrons, reaction stops. Reaction is done. Now we're evil, and we are removing them. Here's the last bullets here. So it's this big, significant jump in ionization energy between removing the second and third that makes magnesium have a stable +2 ion. There are no atoms in nature that have a strong enough force to pull that third one away from magnesium. So magnesium stops giving them up because it just hangs on so tightly to the others. So here you can see I'm expressing the third ionization energy has a greater than the second ionization energy compared to the first ionization energy, which is why that doesn't happen under chemical situations. We can rip it off with a machine, but not in a chemical reaction. That's for magnesium, my example. If I was talking about aluminum, which ionization energy would be the big jump? Which ionization energy would it take a lot more energy to remove? Atlee? The fourth. One would fall off. Second one not fall off, plucked away. Second one plucked away. Third one plucked away. We're back to here. Now we're back again to the second. It's going to be a lot of more energy to pluck that away. So aluminum chemically only gives up 3 because nothing can pull away that next one. If I was talking about sodium, which ionization energy would be the big jump? The second one. First one comes off, stable. Second one, a big pull. Okay? And that's why we have +1, +2, +3, because of the amount of energy it takes to remove them. Just waiting for the last few people here. I've got a couple of examples here in terms of questions. Don't write these down. You have examples of them on your sheet. I just want to talk about them, all right? I just want to kind of verbally go through them so then you know what to expect when you encounter the worksheet. And then I do have one more thing I've got to talk about, and it won't take long, and it's called metallic character. And then I might show you some demonstrations in a little video here. So, 1 second here. Oh, yes, I do want that written down. Sorry, there is a large jump in IE after the last valence electron has been removed. Sorry about that. Okay, again, don't write these down. I just made up some numbers. They're probably not correct ionization energies. Don't worry about the units. Kilojoules per mole. Joule is an energy unit. Mole, you haven't learned about that yet. You'll learn about it halfway through the course. Don't worry about it. Here's our ionization energies. 600, 1800, 10,000. Why is there a large jump between the second and third ionization energies? Why is there this big jump between them? Chris, what do you got?
Third ionization energy, electrons
From a full, I guess it's an outer shell now that it's been removed, but yes, from the next full orbit in. Correct. It's being taken away from that full shell, which is closer to the nucleus. Excellent. What group is this element in? Which of our groups is this element in if it had ionization energy like that? Chelsea? Sorry? Noble gas? Nope. Noble gas, they're not going to give up electrons very easily at all because they already have a full outer shell. Which group? Yep. Excellent. I like to use the term. I would have taken group 2, but you're exactly correct. Group 2. Because one comes off fairly easy. Second one comes off fairly easy. Third one comes off a lot of effort. Alkali earth metals is correct. Okay? Group 2, because the first two come easiest. All right? The electron configuration for the following elements are given, which have the lowest ionization energy, highest ionization energy, right from lowest to highest. Okay. If you're given a question like this, I would put a chemical symbol for it. What element has the electron configuration 2-2? Yep. Beryllium. 2-2. Correct. 2-2. Very good. Beryllium. Be. So really, when I get a question like this, I'm putting it on a table so I can get a visual representation of what's happening. 2-1. Yep. Lithium. And 2. Yep. Helium. Which is going to have the lowest ionization energy? The easiest to remove the electron. Yep. Beryllium. Beryllium. As I move across the periodic table, what happens to the number of protons? What happens to the electrostatic force? Gets stronger. What happens to the ionization energy? Gets greater, harder to remove. No, beryllium doesn't have the lowest. Nope. Yep. Lithium, I agree. It's got the most orbits, and it's got the least protons in the row for those orbits. Lithium is the lowest. Which one has the highest ionization energy, do you think? Yep. Why is that? Yeah, its outer orbit is completely full. It's got a couple of protons in the nucleus and only 2 of them there. It's a noble gas. It doesn't like giving up, right? Well, I know I just said that it doesn't like it, but, you know, that still works. Helium. Once we've determined lowest and highest, rank from lowest to highest, really? Is that really needed? That's a silly question. Libehe, okay? But when answering a question like that, put it on the table. Put it on the table. Ooh, what has the highest second ionization energy, do you think? Which one is it going to be the hardest to take off the second electron? William, what do you think? Why is that? It's now in that inner orbit, and it actually has an extra proton compared to helium, so it's going to hang on to it even tighter. Lithium is correct. So that was to rank right there. The highest second, lithium, because it's in group 1. That second one's got to come off that inner orbit. Excellent job. Okay? Okay, good work. Oh, I'm not worried about that one right now. And first 3 elements, we did that one. Why did I have that? I've got the exact same question. You can now do the sheet, and I do have one more thing to talk about. I apologize. I have to talk about metallic character, but it won't take long. Yes. You can have this one in a moment. Sorry? Yeah, you're going to be writing something for metallic character. It's just one slide. You now can do ionization energy and multiple ionization energies. And when I'm done this slide on metallic character, you'll also be able to do the metallic character part. But metallic character is directly related to ionization energy, and it is very easy to transition between the two. So we're really not going to learn too many groundbreaking things. Let's write down the metallic character note, and then essentially we're done. Looking at the time, 36. This demonstration you've seen, I've got a little bit of a video I can show you. It's kind of entertaining. Maybe we'll do the video to finish off for today. 36. Now we might be able to show you just a little bit. Yeah. Oh yeah, I can show you the stuff. You might be able to take the logic from above and fill in the blanks. Oh, I just moved the cart, which means I'm going to be up. That's all right. Ionization energy describes how easy or hard it is to remove the outer electron. It has everything to do with electrostatic force. Metals tend to lose electrons. A good metal loses electrons very easily. So our good metals, metals that have good metallic properties, the properties of typical metals. They conduct heat well. They are malleable and ductile, which means you can smish them out, so you can roll them out into a flat sheet or stretch them out into a wire. You're able to bend them, right? They're highly reactive. Good metals that have good metallic properties react. They're very reactive. That might not be a desire for if you want to build a car. Like if you want to build a car, you're going to want to build it out of a metal that doesn't react too much. But that's technically not what chemistry describes as a good metal. A good metal is one that has all those metallic characteristics to the highest degree. Metal elements tend to lose electrons easily. This means that they have a low ionization energy. The most reactive elements, metallic elements on the periodic table, are therefore on the blank side of the table. Where will they be found, Christopher? On the left, because the left has the lowest ionization energy. They have the fewest protons in the nucleus, so they are found on the left side of the periodic table. The least reactive elements, therefore, are on the right side. All right? There's even a top and bottom relationship. Where am I going to find the most reactive metals? Where is the lowest ionization energy when I move up and down the periodic table? Where is the lowest ionization energy? Yep, at the bottom. More orbits, farther from the nucleus, very weak hold. Therefore, what is the most reactive metallic element? Most reactive metallic element. Emily was looking at the table. She was having a glance. What do you think? FR, perfect. Francium, all right? Now, francium is made in a nuclear decay reaction. It's very unstable. Francium is not found very easily in nature. So really, cesium, in terms of one that we can get a hold of, is the most reactive, all right? Okay, so when you do an argument to say which element is more metallic than the other, say for that question sheet for the metallic character, what you're arguing is what has the lowest ionization energy, okay? So you'll simply do low ionization energy. I'm going to put that down as one last little thing on the bottom here. Low IE, good metal, or most metallic. All right? So when your question asks, which is the most metallic, you're thinking, which one has the lowest ionization energy? You go through the exact same argument, except at the end, you tack on, right, therefore has the lowest ionization energy, therefore is the most metallic. And you've got it. Okay. Let me just stop this here for a moment. Stop.